Swayam Prabha. Digital India. Educated India.
Let us begin our week 7 discussions from this lecture. In this week, we will spend time on discussing about hypersonic non-equilibrium flows. As we get into that discussion, it will be very useful if we quickly recapitulate the week 5 and week 6 contents. So, we will begin with that. Then we will discuss about some basics of kinetic theory of gases, which you might have already covered in your undergraduate courses in the earlier years, and also as a part of your +2 physics to some extent. We will look at vibrational rate equation, chemical rate equation. So, this is where the rate equations come up when we are talking about non-equilibrium, and we will also briefly discuss about high temperature air in chemical non-equilibrium as we end the week 7 discussions. So, let us begin with a quick recap of week 5 and week 6 contents, especially keeping in mind the concepts which will be essential from the perspective of week 7. If we recall, in week 5 we dealt with equilibrium chemically reacting flows. We dealt with the thermodynamic system as composed of a continuous substance that interacted with its surroundings through work and heat transfer. In that week, we had initially looked at the compressible boundary layer forming over a flat plate, and we did some boundary layer calculations to get an idea about the heat flux and drag acting at high Mach numbers, and consequently why we need to look at high temperature reacting flows in the context of hypersonic Mach numbers. We had reviewed the first and second laws of thermodynamics, and then we went on and introduced the perfect gas equation of state. We started with a pure gas and then we extended it to a gas mixture, appreciating the fact that as a chemically reacting medium would have a number of different species, we need to look at it from the angle of a gas mixture, and this is what commonly happens in course of the chemical reactions which take place. The perfect gas equation was expressed on a mass basis, mole basis and particle basis subsequently, and in this table we have a quick recapitulation of what we had done in that week in terms of the different forms of the equations of state, which are so very useful. Then I am sure you recall that we extended it to a gas mixture, and then we discussed about partial pressure of the different constituent species of the gas mixture and how Dalton's law comes in that sense, in that perspective. And then we discussed about many other parameters which are of interest, like mass fraction, mole fraction, and then we learned how to express the different important parameters in terms of these fractions. We learned how to express, for example, the molecular weight of the gas mixture in terms of its constituent species. Sum of the fractions when summed over all the species went to the value of unity, as you can see over here. For example, for the mole fraction and the mass fraction, the summation goes to 1, while when we sum on different species the partial pressure, it goes to the total pressure of the mixture. So, we became familiar with the mixture starting from a pure species going over to a combination of pure species forming the gas mixture. Then we learned how to derive an expression for entropy of a gas mixture comprising of the different pure species. So, we ended up deriving an expression for entropy in this manner. So, here it is expressed in terms of per mole of the mixture for an equilibrium chemically reacting gas mixture. So, this term equilibrium is emphasized over here, while when we discuss more on the week 7 contents, remember that we will gradually qualify the discussions to a non-equilibrium domain, which is of significant interest in the context of hypersonic flows. And as we moved on with the discussions, we found that the Gibbs free energy is a very, very important concept that we need to introduce in order to deal with chemical equilibrium. So, we derived a condition for equilibrium chemically reacting gas mixture in terms of the Gibbs free energy, and this equation was ultimately very useful in finding the composition of the mixture when equilibrium existed. So, you may recall that we wrote the different chemical reactions generically in a form like this, where the reactants were taken over to the right hand side of the equation along with the products, and therefore, we adjusted the number of moles of the reactants. The sign that they earlier had was positive when they were showing up on the left hand side of the equation as reactants, but when they moved on to the right hand side, they had a minus sign associated with them. And then having expressed the generic chemical equation in this manner, we went on to calculate the difference in the Gibbs free energy between the products and the reactants, where the reference pressure was set to 1 atm. So, that is why we have the superscript provided as P equal to 1 over here. And then we found that when we looked at the partial pressures of the different constituent species which took part in the chemical reactions, then those partial pressures, when they were raised to the index of nu y and we took the product of those, we got an expression like this in terms of the change in Gibbs free energy showing up on the right hand side. And using this form, we came up with the concept of K p, which was a function of T, that is the equilibrium constant. Since the P was fixed, K p happens to be just a function of temperature. So, this is how we went on to get expressions for the equilibrium constants for the different chemical reactions that were of interest to us. And then we gradually started appreciating that these tools would be very much essential if we were to calculate the equilibrium high temperature air chemical composition, and if we were interested to do it for a wide range of temperatures that might be encountered during a hypersonic flight. We set the pressure to 1 atmosphere to see the temperature variations for the different phenomena which occurred, and for 1 atmospheric pressure we found out the different temperature ranges applicable for air in terms of vibrational excitation, dissociation of molecules, ionization of atoms. The primary interests remain on the molecular nitrogen and molecular oxygen, which first after the vibrational excitation start dissociating, then there is combination of the atomic forms, further there is ionization and so on, and some of the very important relevant temperatures are marked on this plot, which I am sure you must be recalling very well. We further discussed about the concept of heat of reaction, and we figured out that this is another very important concept in terms of understanding the chemical reactions. And you may recall that we took an example chemical reaction of this form, and then we said that the reactants, let them be at some reference temperature T ref, and at this temperature we summed the total enthalpy, and we allowed the chemical reaction to take place at constant pressure. And finally, we either extracted or added enough heat from the thermodynamic system comprising of the products, which would bring the products to T reference temperature. So, we had to extract heat if it was an exothermic reaction, we had to add heat for an endothermic reaction in order to bring the products to T ref. And the heat that was extracted or added from the thermodynamic system was called as the heat of reaction. And this heat would actually raise the enthalpy or reduce the enthalpy, because everything was happening in an isobaric condition, that means constant pressure. Hence, the heat transfer is equal to the change in enthalpy, and heat of reaction at the reference temperature was thereby indicated as delta HR T ref. So, we finally came up with a change in delta HR at T ref, taking the enthalpy between the products and the reactants at the T reference temperature, and we finally expressed it in a form like this. So, the delta HR T ref value, we said that it can be calculated from either the Janov tables or from statistical thermodynamics. We will try to find time to work out a problem down the line, where we can get deeper into the concept of heat of reaction, which would be really interesting. Then we move on to some of the topics of week 6, where the broad purview of week 6, as you may recall, was that we took a more microscopic point of view in this week of the thermodynamic system, and we inspected the system as made up of individual particles with different energy modes, namely translational, rotational, vibrational and electronic energy modes. We also realized that the macroscopic properties of the system are simply reflections of suitable statistical averages over all of the particles. So, this week's content was also enormously important, and we will find that as we move along with the discussions of week 7, how important these concepts would turn out to be. So, this is a good point to recall the different molecular energy modes. So, we looked at the translational form, and we remember that it applies to both molecules as well as atoms, and I hope you are able to recall how many degrees of freedoms are involved here. We often refer to them as thermal degrees of freedom as well as geometric degrees of freedom. Another form of energy which is common to both atoms and molecules was the electronic energy, and we found that these energy levels are essentially quantized. In one of the later slides, we will be recalling that fact once again. And after we look at the electronic energy, we are still left with another 2 energy modes, which are specific to molecules alone. So, one is the vibrational mode, the other is the rotational mode, and thereby when you sum up, you find that for atoms the total energy would come from the translational and the electronic modes, while for the molecules it is of course translational and electronic, but additionally also rotational and vibrational. One of the things that we will be doing in week 7 is to look at vibrational non-equilibrium, and therefore, it is essential for us to recall all these things from the statistical thermodynamic point of view, because these concepts will be really useful for us in this week's discussions. We recall about the very important energy level diagrams. So, here what did we learn? We saw that the different energy levels were quantized. So, that was the first learning here, the quantized levels, and then we found that the translational energy levels are spaced very closely with each other. That means, the quantized energy levels are very close to each other, in the sense that the changes across one energy level to the other was very small. They almost look like a continuous distribution of energy, and for each one of the modes we find we have the base level, and that is indicated in the form of a epsilon 0 dash and followed by another subscript, let us say translational or rotational, vibrational or electronic. So, we recall about the 0 point energy, and then when you look at the relative picture between the different energy modes, you find that there are distinct differences. The rotational energy modes from one level to the other involve much larger jumps compared to the translational mode, and at the higher energy levels the jumps become larger and larger. In the vibrational case, again you have the jumps larger than the rotational, but the first jump is the largest and the later ones at higher energy levels they get closer to each other. Electronic in a way is similar to vibrational in the sense that the first jump is the largest one, subsequent ones get a little lesser, but the electronic energy jumps from one level to the other are significantly larger than the other energy modes. So, I am sure you very vividly remember this energy level diagram, which is so very important for us. Then we came up with the concept of thermodynamic equilibrium from the point of view of statistical or microscopic thermodynamics. We said that for a system of n molecules or n particles which has an energy capital E comprising of all the energy contributions of the n particles, let there be a series of quantized energy levels. So, these quantized energy levels are essentially coming from the sum total effect of all the different energy modes which lie in those molecules, and we also talked about corresponding statistical weights. So, there were the energy modes as well as the energy states, which I hope you are able to recall. At a certain time instant, let the molecules be distributed over the energy levels with a certain population distribution. So, starting from the lowest energy level onwards, you have a certain population distribution. With the given population distribution, you are able to define what is called as a macro state. So, macro state is connected with the population distribution. That is something that we have to remember very carefully. And then we have to keep remembering that as we are looking at the microscopic levels, there are molecular collisions which are going on all the time. So, for the very next time instant, the population distribution may be slightly different compared to the earlier instant. The populations of some levels might have changed without, of course, changing the total population, because the total number of molecules or atoms, they remain conserved anyway. This would lead to a different set of nj values starting from n0 to n1 and so on. You will have different numbers now. Therefore, it gives rise to a different macro state. In this manner, if we follow the thermodynamic system over a period of time, we might find that there is one particular macro state which repeats more often than any other, and this is called the most probable macro state, and it occurs when the system is in thermodynamic equilibrium, which means of course that when the equilibrium breaks down, it would be difficult to find one of the macro states repeating distinctly at higher frequencies than any other. And then we saw that from a statistical thermodynamics point of view, the problem basically reduced to finding the most probable macro state for a fixed number of identical particles n and their total energy defined by capital E. So, when we tried solving the problem, we realized that we also need to define something more than what we already have. That is what gave rise to the need for a micro state, and that is where we remember we brought in the statistical weights or the degeneracy, and we also started discussing about two different statistics to handle this problem. So, one of the statistics was the Fermi-Dirac statistics, meant for molecules and atoms with odd number of elementary particles, and The rule in this case was that they can populate the degenerate states in such a manner that only one particle, which may be a molecule or an atom, can occupy one particular degenerate state. And you may recall that we defined the degenerate states in the diagrammatic sense in the form of boxes. You see the different quantized energy levels, you see the population distribution, the number of particles assigned to each energy level at a given instant of time when you are observing the system. Then you see the degeneracy level of that particular quantized energy level, and you open up that many number of boxes here to be filled by the population that you have at that energy level, the number of particles that you have there, and therefore you start filling boxes following this Fermi-Dirac statistics rule that only one per box at most, and thereby you could have numerous microstates this way. And then as the microstates become larger and larger, there may be one particular macrostate where the microstate gets number of microstates gets maximized. We also looked at the Bose-Einstein statistics, which was applicable for even number of elementary particles, and then here the rule was that the particles could populate the degenerate states in such a manner that more than one particle can occupy a particular degenerate state, and therefore you could see boxes where more than one particle has got accommodated. So this gave rise to the Bose-Einstein statistics, and we call this as a microstate 3, distinguishing it from the microstate 1 and 2 as was shown before, because the statistics rules were distinctly different. But then we found that there was a situation where both the statistics would actually converge. Also, the particles which were following the Bose-Einstein statistics, we call them as bosons. The other family, the Fermi-Dirac statistics family, as fermions. We counted the number of microstates by following the usual rules of probability, and we found that this was the relation for the number of microstates in terms of the population distribution and the degeneracy at each level j for bosons, similarly for fermions, and W was called as the thermodynamic probability, as it is a measure of the disorder of the thermodynamic system. We found that both the Bose-Einstein as well as Fermi-Dirac statistics converge to a single statistics which was proposed by Boltzmann, a population distribution of particles which works in the high temperature and low pressure limit, and therefore most useful for any kind of aerodynamic applications which we are looking at. There we found the population distribution with a star on top, which indicates the Boltzmann distribution, with the partition function q in the denominator of that relation. We later on found that the different thermodynamic variables can be expressed in terms of the partition function q. We demonstrated it for internal energy, enthalpy, pressure, entropy, etc. We then recalled about some of the quantum mechanics results for obtaining the sensible energies in different energy modes. You may recall that the sensible energies are the ones above 0 point energy. So, this is an important equation to indicate the distinction. So, if you lump all the 0 point energy into this term and you set the rest apart, then that rest portion basically will contain the sensible energy, which is the measure above 0 point energy, and which corresponds to temperatures above absolute 0. This approach helped demonstrate how the thermodynamic properties of a single chemical species gas can vary over a wide range of temperature due to excitation of various energy modes. So, we could show that for atoms, the CV, for example, the specific heat at constant volume, can be shown to be varying like this. It is 3/2 times R, the specific gas constant, plus the partial derivative of the electronic energy, the sensible energy content with respect to temperature. For molecules, you had that as well as this part repeating from the atomic form. Additionally, you had the energy contributions from the rotational as well as the vibrational part. So, the 3/2 R was basically coming from the translational part, if we recall, and we could show that the vibrational part had a dependence on temperature, and therefore, as temperature increased, the CV would become a function of temperature, and that is how we started distinguishing the behavior of the gas, beginning with say a calorically perfect gas to a thermally perfect one, where from a constant value of CV as a function of temperature, the CV became a function of temperature in the thermally perfect regime. At still higher temperatures, of course, the medium would become chemically reacting, and then there may be massive variations in CV. This was a nice graphical demonstration of how CV changes as a ratio of CV by R, where the numbers on this axis are extremely important to be appreciated, and this axis, of course, though it is not a linear axis, it is kind of a logarithmic axis. You can figure out how over the temperature range the variations come up, and why do they come up, in which portion is gamma constant, in which portion does it become a function of temperature, and why all these changes are happening. So, these learnings helped us understand how air, which is basically a mixture of some pure gases predominantly like N2 and O2 at normal conditions, would start behaving differently if the temperature was elevated. We then looked at the equilibrium composition of high temperature air and over a wide range of temperatures. If you remember one of the diagrams that was of interest to us, where we looked at the vibrational energy excitation of air at around 800 Kelvin, and then gradually the dissociation of oxygen starting from about 2000 Kelvin, etc. So, such things can be directly calculated or computed if you follow a certain procedure by including the relevant chemical equations of interest over the range of temperatures that is of interest to you. So, here we set out with a goal of trying to look at equilibrium composition of high temperature air over a range like 2500 Kelvin to around 9000 Kelvin, and therefore, you would remember that that range is sufficient to bring about dissociation of molecular oxygen, molecular nitrogen, formation of NO from the atomic nitrogen and oxygen, and then dissociation of NO into NO plus and free electrons, and so on. We realized that there could be multiple species. Here it is predominantly 7 that we looked at, and there was an issue of finding the partial pressures of the different constituent species. We realized that that would also lead to setting this condition that the sum of the partial pressures should be equal to the total pressure, and when the total pressure is basically an input parameter, the partial pressures get scaled according to that. Then comes the use of the equilibrium constant, which in the box on top right also shows the way we proceed to calculate it from the partition function in statistical thermodynamics, and therefore, for the different chemical reactions that we saw on the previous slide, you would be able to express the equilibrium constants in terms of the partial pressures of the reactants and products raised to suitable indices, keeping in mind that the generic chemical reaction is taken in such a manner that the reactants go over to the right hand side. And then there was the mass balance equation, where we made sure that the number of nuclei of oxygen and nitrogen which participated in the reactions, they remain conserved and then came the electric charge conservation, where the participating species were NO plus and E minus, their partial pressures need to balance. So, all these gave rise to 7 nonlinear simultaneous algebraic equations, which should be sufficient to solve for the 7 unknown partial pressures. And we also came across a rule that if there are sp number of species and any number of elements, then we need sp minus any number of independent chemical equations. That independent word was stressed adequately, and thereby based on this we had actually taken 4 independent chemical reactions to model this problem. So, if we were to solve this problem numerically and then try to show the mole fraction of the different species at 1 atmosphere pressure over a temperature range, we should be able to get a result of this form. Again, we noticed here that if pressure was increased substantially, then all these mole fraction variations would shift to higher temperatures and vice versa. So, a wide range of concepts were actually discussed in weeks 5 and 6. These concepts are of enormous importance and of use for the different topics which we would be discussing in week 7 contents, and therefore, a recapitulation was absolutely essential at this juncture. Now, in the upcoming lectures of week 7, we shall be discussing the basic kinetic theory of gases, where we discuss concepts like particle velocity and speed, particle translational energy, collisions, frequency of collisions, mean free path, and so on. And these concepts would be important when we discuss vibrational and chemical non-equilibrium in the later part of week 7. The foundations of many of these concepts were covered in week 5 and 6, and therefore, this discussion was really useful for us. Thank you.